So, hello guys, hello. So, I'm back. I'm back with another study session. Let's go and study. So, previous stream we left these chapters matters versus in previously we left this chapter, right? We didn't do the exercises like matter in surrounding us, matter in surrounding us, matter in our surroundings. This chapter we didn't do the previous lesson, right? So now we're doing the exercises. We already did the full chapter. Yeah, this box we missed that day. So sorry, over this because of the mic, right? So quantity or so these are the units you you will be using units in this chemistry. So you remember this is the basics units. So quantity like temperature. If temperature say any numericals, you have to use Kelvin, and Kelvin short symbol is K. Like length, quantity length, unit is meter, symbol M. Mass unit, quantity mass, unit kilogram, and symbol kg. Weight, quantity weight, unit Newton, symbol N. Volume, quantity volume, unit cubic meter, symbol MQ. Density, quantity density, kilogram per cubic meter, symbol kg, M minus 3. Quantity pressure always be measured by Pascal, PA symbol. So density we measure kg meter cube minus 3 cube, and volume cubic meter m to the power 3, or you can say mq meter cubic meter. Weight Newton, we always Newton. Mass kilogram, kgs. Length meter m, and temperature Kelvin K. So now if I go to the exercise say convert the following temperatures to the Celsius scale, right? So here says convert the following temperature to the Celsius scale. Now, oh, this timer is going on, so it's where now. Now I'll be using here. Now I'll be using here that question. What it say? Convert the following. So I have two. Option A is option A have 293 Kelvin, and option B has how much? 470 K. Okay, okay, 470 K, right? Now, so how to solve this question? So all there's a formula. What formula? For T bracket degree Celsius equals to T minus K. In this T you remember, this T is, sorry, where did it go? I made a mistake right here. So basically this T is K and minus 273K. So now you all know, right, that 273 Kelvin equals to 0, but that's not true. So I am here doing some rough work that's showing you that 273K not equal to 0, but many teachers use that 273K equal to 0. Not, it's not, because 273K equals to 0.15 minus 0.15 minus, it's not 0 degrees Celsius, it's lesser than that. but we can say 273 Kelvin, this approx 0, then we can use it's a 0 degree C. So that's the thing, it's not equal to, always remember 273 not equal to 0 degree C. So now we will calculate this 293K, right? So what will we do? We will do basically use the formula. Say they ask for degree Celsius, right? So we 293K minus 273K we will doing. So we'll get how much? 20. We are getting 20 degree here. 20 degree C. And second one 470, right? 470K. So 470 minus 273. How much? 307, then 188 and 17, 9 and 197 degree C. So the answers are basically answers are they see answers are 20 degree C and 197 degree C. So I calculated both these questions. Now the second one, convert the following temperature into Kelvin scale. So now they are saying that convert to Kelvin scale from degree C to Kelvin. So how can do it? How we can do it? Convert the following temperature to Kelvin scale, right? So first 25 degrees C. If we are using 25 degrees C here, 25 degrees C, we can assume it. Now that formula we have to use. So here they are asking for this T. They are asking for this T, and they are given me this now. So I will transfer. So I will transfer this to this side because it's a equation, right? We know how to solve equation. So I will transfer it to this side. So if I transfer to that side, 25 degrees C, if we convert to Kelvin, how much it will? It will be 25 degrees C. So basically 273 plus 25, how much? It will become 270 plus 20, 290, 295, 298 Kelvin. So directly I am writing here. No, you will not understand then. Okay. So 25 degrees C here and minus 273K equal to TK. Now I'm for this I calculated it here 297K for 25 degrees C. So I'm using this 298K minus 273K equal to TK. Now how much it will? So sorry, it will be plus. So now 298K. No, I am doing something wrong. Why? Because they are asking simply 25 degrees C how much. So just add 25 degrees C into 273, you will get it. Yeah, the answer will be this. The answer will be this 298K for 25 degrees C, 298K. And the second one is 373, right? 373 degrees Celsius means 373 degrees Celsius. Oh shit. Means 373. 370 C. So if I have to do it, then we have to add 373 to Kelvin. They are asking to transfer into Kelvin. Just add them out. No, we cannot add them. Just add them out. Why? Because it's a 373 degrees Celsius, right? So if we add them, we cannot add them here. So what we have to do? We have to do just 273. We know 0 degree C is 273, so it's 373. So just add them. 3 threes are 6, 7 sevens are 14, 1, 3 threes are 6, 646 Kelvin. So one is 298, one is 646. Sorry. Oh, what am I opening? So where is the answers? They didn't give the answers right. We'll find out about answers. So what? Give the answers. I want to know the answers. Yeah, I'm right. You see, 298 and 646. As simple as it. Just add them up with 273. If they're asking Kelvin, just minus them by 273. That's it. That's the basic rule. But that formula also important. Always remember that formula also important. Here from formula you can do it, but here I have a mistake. I have made a mistake here because I am converting to 25 degrees C, but that's not needed. You can do like that. This line you forget, and then you will get your answer. So you'll get your answer here, 298K. Remember? Let's go to the next. So now give reason for the following observation. Okay. So naphthalene balls disappear with time without leaving any solid. Okay. We can get the smell of perfume sitting several meters away. Give reason for the following observation. So naphthalene balls disappear with time without leaving any solid. We can get the smell of perfume sitting several meters away. So what happens here? So if you want to know, give the reason for the following observations. Naphthalene balls disappear with time without leaving any solid. Yes, yes. We can get the smell of perfume sitting several meters. Yeah, also no. So this will, that question also I'll need answers. Why it's happened? So what they will give us answer. Let's see. छुपा सको तो छुपा लो. What's happening? So they give us the answer already. What answer they give? So they give the answers. Let's see what they're saying. So naphthalene balls disappear with time without leaving any solid because the reason naphthalene undergoes sublimation. So now sublimation, you got the sublimation. Now I'm telling. So the reason The reason is that naphthalene disappear from solid form to gaseous form. But solid form gaseous, that is called sublimation. We already learned the chapter. Sorry for that. So we already learned about sublimation, right? If we see sublimation here, there, this sublimation. See, so this is the sublimation. What it say? Sublimation is the change of solid state directly to gaseous state without going through liquid state. So that's happening with naphthalene. Naphthalene solid. If in your home, I will assuming that in your home naphthalene also there. So we use naphthalene to in our drawers, almaris. So why? Because our clothes. So for protecting our clothes from fungus or any other bacterias, because that smell or that solid form of naphthalene can protect our clothes. So that naphthalene is a solid form, right? When you open the seal pack and you use to and mm, you take the naphthalene and put it to your almaris or drawers. Now after 15-20 days you can see that naphthalene became so much small. Why? And no liquid is there. Why? Because sublimation is change solid to gaseous state without becoming a liquid form. So direct they convert to solid to direct they convert solid to gaseous state. That's called sublimation change. So the second one also says that we can get the smell of perfume sitting several meters away. How? Here says we can reason perfume particles spread through diffusion. The gas particle from the perfume move rapidly and randomly, mixing with air and reaching distant places due to their high kinetic energy. So, so this how we can get the perfume smell. Perfume particles spread through diffusion. So when did diffusion happen? So here also diffusion, they told about diffusion, right? They have told about diffusion, deposition layer, gaseous state directly to solid. This is not phenomenon. This is also not evaporation in surface phenomenon. Particles from surface gain through. This is not what I'm looking for. I'm looking for the diffusion. Diffusion. Are you not telling diffusion about diffusion? Evaporation. I don't need evaporation. Dish. No. Fusion, solid to liquid. This is not what I'm looking for. I'm looking for diffusion. So if I use CF, it will show me diffusion. Where is diffusion, bro? There is no diffusion. Hmm. One is here, but where? Another is here. Here. So here is diffusion. So activities we observe that particles of matter intermix in their own with each other. They do so by getting into the space between the particles. This intermixing of particles of two different types of matter on their own is called diffusion. So this intermixing of particles of two different types of matter on their own is called diffusion. We also observe that on heating, diffusion becomes faster. Why does this happen? So diffusion says they do this intermixing of particles called diffusion. Intermixing of particles of two different types of matter on their own is called diffusion. There here. Thus here I find it. The smell of hot cooked food reaches us in seconds. Compare this with the rate of diffusion of solids and liquids. Due to high speed of particles and large space between them, gases show the property of diffusing very fast into other gases. In gaseous state, particles move about randomly at high speed. Due to this random movement, the particles hit each other and also the walls of the container. The pressure exerted by the gas is because of this force exerted by gas particles per unit area on the walls of the container. So that's how happen. So it's saying diffusion here also your diffusion. Thus we may conclude that solid liquid gases can diffuse into liquids. The rate of diffusion of liquid is higher than that of solids. This is the due to the fact that the freely and have greater space. So in gases, in gaseous states, thing is that diffusion happen more fastly. Why? Because because the smell of, if assume if you assume the smell of hot cooked food reaches us in seconds. Why? Compare this with the rate of diffusion of solids. Compare this rate of diffusion of solids and liquids. Due to high speed of particles and large space between them. So you already saw that solid, liquid and gas. So solids particles are very close to each other and there are no space between them. But in liquid there is minimal space, and in liquid the particles are moved freely, right? But in gaseous the particles are moved freely with high speed. Also the space between them very big. That's why the gaseous forms particles hit the wall. If you cook the food, here it says due to high speed of particles and large space between them, due to high speed particles and large speed between them, gases show the property of diffusing very fast. So gases show the property of diffusing very fast. Diffusing means when it diffusing means, if you want, that's the main problem. Diffusing means, we want to know diffusing means so you can get it more clearly. What diffusion means we want to know. So diffusion means the process by which particles of matter move from a region of higher concentration to a region of lower concentration until they are evenly spread out. You are getting it? So it's the main thing. So they are saying that diffusion means when the particles of matter move from one region to another region very fast. A matter move from region of higher concentration to lower concentration until they are evenly spread out. So what they do? The particles of matter move from higher concentration to lower concentration until they evenly match or spread out. So it says diffusing is basically particles movement. So solid, liquid and gases, these three type also shown the diffusion. These three also shown the diffusion, but the gaseous diffusion is very fast. Why? Very fast and the particles have bigger gap between them. So they go from higher concentration to lower concentration to spread out. They spread out. That's why we feel the smell of cooked food or perfume, because they quickly spread out. That's called diffusion. Now go to the questions. That's done. Now arrange the following substances in increasing order of forces of attraction between the particles. Water, sugar, oxygen. What? Arrange the following substances in increasing order of forces of attraction between the particles. Water, sugar, oxygen. Okay. Increasing order of forces of attraction. Increasing order of forces of attraction. Okay. So water, sugar, and oxygen, they are saying attraction, increasing force of action. So attraction between particles. So sugar is the first one. Second one is water, and third one is oxygen. Now what is the physical state of what is the physical state of water at 25 degrees C, 0 degrees C, 100 degrees C? 100 degrees C, it's become gas. Everyone know that. 100 C, water become gas. 0 degrees C, it's become solid, because ice, it become ice cube. And 25 degrees C, it's become what? It's liquid. It will not become gas, it's remain liquid 25 degrees C. So this is also give two reasons to justify water at room temperature is a liquid. Give two reasons temperature. Okay. So water at room temperature is liquid. Yes, because the room temperature always between, you can assume room temperature will be always between, if I give you a vast 15 degree, like Indian, it's always 22, 30, 38, or in the summer days it become 40, 45. But that's all. You suggest 50. I feel 50, 15 to 50 is room temperature. That's why, because two reason they are asking for two reason. So two reason is that water in 0 degrees Celsius become solid, and 100 degrees Celsius water become gas. So that's the justification that the water room temperature is liquid. Without the that's the minimum temperature. If it's get 100 degrees C temperature, it will become gas. And if it get 0 degrees C temperature, then it will get solid. These two are the reason. An iron, now an iron amalgam, sorry, an iron amalgam, sorry. Sorry, sorry for the inconvenience. I'm back, I'm back, I'm back, I'm back. So now, so what I'm saying, no, 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 now go to the topic. So I give you the what is the room temperature is called, right? I already told you. So now what? So an iron almirah is a solid at room temperature. Yes. So give two reasons to justify. What the fuck? Sorry, sorry, sorry. Don't use abusive. So an iron almirah is a solid at room temperature. So it will become solid. An iron almirah is solid in room temperature. Yes. Yes. Because for an iron need I guess 1000 degrees Celsius to it become liquid. That's why in room temperature iron will be solid. It will not be changed. So if I want to know the reasons, I can ask for what reasons they will give. Let's see. So the reasons is moderate. So first reason is water molecules are held together by forces that are strong enough to keep them close but weak enough to allow flow. Fluidity or flexed. At room temperature 25 degrees C, water maintains a fixed volume but takes the shape of its container. Key properties of liquid. What this water at room temperature is liquid. Yes, water molecules are held together by forces that are strong. They are saying water molecules held by forces that are strong enough to keep them close. That are strong enough to keep them close but weak enough to allow flow. And fluid and fixed volume at room temperature 25 degrees C, water maintains a fixed volume but takes the shape of its container by properties of a liquid. Now the almari. So almira is solid at room temperature. So strong intermolecular forces. So iron atoms are tightly packed. I already told you that solids are tightly packed, but they don't have spaces between them. Very strong forces give it a rigid structure. Definitely say by volume, right? So the almira retains its shape and volume regardless of the container or environment, which is the characteristic of solid. So basically, they want us to give liquids characteristics, and solid characteristics, two characteristics. That's all. So now, why is ice at 273 K more effective in cooling than water at that same temperature? What? Why is ice at 273K more effective in cooling than water at the same temperature? What type of question you are asking? This is a because ice cube are more cooler. 273K water became also a ice cube. Water become will be ice. So here's why. When ice melts at 273K 0 degrees C, it absorbs additional heat from its surroundings without increasing its temperature. Okay, this hidden heat is used to change its state from solid to liquid. Water already in liquid form, it doesn't require extra energy to change state, so it is only absorbs heat based on its temperature, not as effective for cooling. Okay, that's why. So guys, you understand why? Because for ice cube it's become solid, right? So in 0 degrees C it's want to become liquid, so it's want more heat, so it will take more heat from the surrounding us and give the cooling, because it's absorbing the surrounding heat and give us cool. If this absorbing surrounding us heat, then all the heat is gone, then there will be cool somewhere, there will be cool, right? Or temperature low. So that's what it do. So it's, yeah, absorbing heat and changing itself to liquid form from solid. That's why we feel cold, more cool than water, without increasing its temperature. Heat from without increasing its temperature. This hidden heat is used to change its state from solid to liquid. So, but in water, 273 K water, because water already in liquid state, it doesn't need any extra heat to to change to change to liquid, because it's already in liquid. So it will take only those heat according to its temperature. If water is more cool, more if water, it's, so here already said that already in liquid form, so it doesn't require extra energy to change state. So it only absorb heat, based on its temperature. So if its temperature is low, then it will take more heat. If its temperature is not temperature is not high, then it will not take any more heat. That's all. So what produces more severe burns, boiling water or steam? What produces more severe burns, boiling water or steam water? So what produces more severe burns, boiling water or steam water? Obviously boiling water. Steam means though it is vaporized. छुपा सकोगे ओ. I want to see the answers. It will be boiling water. Well, obviously, steam water is the vapor. Latent heat. Steam produces more severe burns than, okay, steam produces more severe burns than boiling water at same temperature. Why? 100 CO 373 Kelvin. Because the latent heat of vaporization. Here's why. Steam carries extra energy. Okay. When water turns into steam, it absorbs additional heat without a rise in temperature. The hidden energy is called latent heat. Upon contact with skin, steam releases this latent heat as it condenses back into water, delivering more energy than boiling water alone. Boiling water, while hot, does not undergo a phase change upon contact, so it transfers less heat compared to steam. So steam will be the answer. Sorry guys for my wrong answer, but steam will be the answer. Because why ice? Why is ice at 273 K more effective and cooler than? So because the what produces more severe burn. So steam water, because it takes more energy and take more heat. That's why if we steam a contact with any skin or skin with skin, then it will give the more burn, severe burns than boiling water. Why do boiling water while? Because boiling water while hot does not undergo a phase change upon contact, so it transfer less heat compared to steam. So name A, B, C, D, E, and F in the following diagram showing change in its state. So from A, solid to liquid. Name A, B, C, D, E, and F in the following diagram showing change in its state. Showing change in its state. Okay. Let's go. Name. So name A, B, C, D, E, and F in the following diagram showing change in its state. The solid to liquid, right? Solid to liquid. and liquid to gas. So A solid, B liquid, liquid to gas. Now C gas, then become liquid. Now F is a liquid, liquid, then liquid to solid D. D is a solid. Sorry, I did a mistake here. So D is the liquid. D is liquid because it liquid to become solid, right? So D is liquid here, and F is different. F gas to solid. F is a solid. No, F is a gas. It's becoming. So F is a gas, right? Becoming solid. So F is a gas, and what is E? E is solid to gas. So E is a solid. That's all. But let me see the answers. हमको तेरे बिना जीना तू सिखा दे मगर चले आना. So मैंने ये लिख दिया ये तुम. So I write the first it's but not it's saying that it's becoming liquid to solid, so you have to write both solid to liquid. That's how you write it. So A solid to liquid, B vaporized to liquid to gas, and C condensation gas to liquid. That's how you write it. So group activity, what is this activity? Dried grains, stretchable rubber sheet string, few chickpeas or black gram, dry green peas. So let's go to the move on to the next chapter. Metal surrounding us pure or not? This is chapter 2. Where come for chapter 2? So is matter around us pure or not? So how do we judge whether milk, ghee, butter, salt, spices, mineral, water or juice that we buy from the market are pure? How? So have you ever noticed the word pure written on the packs? Consumables. For a common person, pure means having no adulteration, but for a scientist, all these things are actually mixtures of different substances and hence not pure. For example, milk is actually a mixture of water, fat, proteins, etc. Right? When a scientist say, when a scientist say that something is pure, it means that all the constituent particles of that substances are the same in their chemical nature. A pure substance consists of a single type of particle. In other words, a substance is pure single form of matter. Pure single form of matter, right? As we look around, we can see that most of other we can see as we look around, we can see that most of the matter around us exist as mixtures of two or more pure components. For example, sea water, minerals, soil, etc. are all mixtures. What is a mixture? So mixtures are constituted by more than one kind of pure form of matter. We know that dissolved we know that dissolved sodium chloride can be separated from water by the physical process of evaporation. However, mixtures are constituted by more than one kind of pure form of matter. So we know that dissolved sodium chloride can be separated from water by the physical process of evaporation. However, sodium chloride is itself a pure substance and cannot be separated by physical process into its chemical constituents. Similarly, sugar is a substance which contains only one kind of pure matter and its composition is the same throughout. Soft drink and soil are not single pure. Soft drink and soil are not single pure substances. Whatever the source of a pure substance may be, it will always have the same characteristics properties. So therefore we can say that a mixture contains more than one pure substance. We can say that because a pure substance and cannot be separated by physical process into its chemical constituents. Similarly, sugar is a substance which contains only one kind of pure matter and its composition is the same throughout. Soft drink and soil are not single pure substances. Whatever the source of a pure substance may be, it will always have the same characteristic properties. So therefore we can say that a mixture contains more than one pure substance. Okay, so type of mixtures. So depending upon the nature of components that form a mixture, we can have different types of mixtures. So now, so type of mixtures, depending upon the nature of the component that form a mixture, we can have different types of mixtures. Okay, what type of? Different type of mixtures, right? Different type of mixtures are, so color of the solution of what the different type of mixtures. Okay, so what are the different types of mixtures? So color of the solution of two groups through both groups have obtained copper sulfate solution, but intensity of color of the solution is different. This shows that a homogeneous mixture can have variable composition. So mixtures are two types of mixtures. That is a two type. I can barely say two type. Barely say means two types. One is homogeneous and one is heterogeneous. Homogeneous mixture or heterogeneous mixtures. These are the two types. In homogeneous mixture we call solutions, but in heterogeneous are two. The one is colloid and one is suspension. So now we are coming to what is a solution directly. So what is a solution? A solution is a homogeneous mixture of two. A solution, what is a solution? A solution is a homogeneous, I already told you homogeneous, right? So a solution is a homogeneous mixture of two or more substances Why we call it a mixture? Because mixture means where we mix different two or more products to a single one, we call it a mix, right? That's a proper mixture. So that's what here it says, that two or more substances mixture. Homogeneous mixture is a two or more substances you come across various types of solutions in your daily life. Okay, so like lemonade, soda water, etc., are all examples of solutions. Usually, we think of a solution as a liquid that. Wait a minute. Wait a minute. 1 minute. Give me 1 minute. Sorry. Okay, I'm back. I'm back. Let's continue. So you came across various types of solution in your daily life, like lemonade, soda water, etc., are all examples of solutions. All example of solution. Usually we think of a solution as a liquid that contains either a solid, liquid, or a gas dissolved so in it. But we can also have solid solutions. Solid solution like alloys and gaseous solutions like air. In a solution, there is there is there is a homogeneity at the particle level. For example, lemonade tastes the same throughout. This shows that particles of sugar or salt are evenly distributed in the solution. Okay, okay. So what is the alloy? So here is more to know about alloy. What is alloy? So alloys are mixtures of two or more metal or a metal and non-metal. Okay, so alloys are the mixtures of two metals or two non-metals, or metal or non-metal. These are called alloys and cannot be separated into their components by physical method. And you cannot separate alloys by physical methods, but still an alloy is considered as a mixture because it shows the properties of constituents and can have variable composition. For example, brass is a mixture. For example, brass is a mixture of approximately 30% zinc and 70% copper. Brass means that product that we make. We make our kitchen utensils in what it say, kitchen utensils. So a solution has a solvent and a solute as its components. So the component of the solution that dissolves the other component in it, usually the component present in larger amount, it is called the solvent. So the component of the solution that is dissolved in the solvent, usually present in lesser quantity, so is called the solute. The component of the solution that is dissolved in the solvent, usually present in lesser quantity, is called a solute. Solute and solution, you got a solute and solution. So I am describing you in a. So what is solute? In solution, right? So what is solute and what is solvent? So let's see. So it's a glass. In that glass, this is the water, and I am taking 1 spoon of NaCl. and mixing in this water. So this 1 spoon is lesser lesser than water. So we call it, so lesser than water, right? So it's lesser than water, we call it a solute. And which is and this water is called solvent. So remember this thing, which is in a solution, which is a lesser amount present in that solution, we call it a solute, and which is a present in larger amount, we call it a solvent. So water is a solvent here. So now go. So now examples, a solution of a sugar in water is a solid, right? In liquid solution, in this solution sugar is the solute and water is the solvent. So a solution of iodine in alcohol known as tincture of iodine has iodine solid. So as the solute and alcohol liquid as the solvent. So aerated drinks like soda, water, etc. are gas in liquid solution. This contain carbon dioxide gas as solute and water liquid as solvent. So air is a mixture of gas in gas. Air is a homogeneous mixture, okay, of a number of gases. Its two main constituents are oxygen and nitrogen. So oxygen gets 21% and nitrogen gets 78%. The other gases are present in very small quantities. So mainly two in gas, oxygen and nitrogen. So properties of a solution. A solution is a homogeneous mixture. We already know that a solution is a homogeneous mixture. The particles of a solution are smaller than 1 nm. We already know that. So I already told you that there is two mixture, right? One is homogeneous, one is heterogeneous. In homogeneous there is a solution, and heterogeneous colloids and suspension. So always remember the solution size less than 1 nanometer, less than 1 nanometer. But colloid and suspension, colloid size is 1 nanometer to 1000 nanometer. Colloids can be any size between them, and suspension size bigger than 1000 nm. Remember that. So concentration of a solution. So ice, because of very small particle size, they scatter, okay. So 10 to the power minus 9 meter in a diameter, so they cannot be seen by naked eyes. Because of very small particle size, they do not scatter a beam. You got it? So they do not, there is a call in the chapter, you will learn about Tyndall effect, right? So Tyndall effect, what is Tyndall effect? When we take a one glass of like 1 glass of milk, and you take a torch and give the light beam to that glass, you will see the small particles are in that light, small particles are scattering the light. We call it a Tyndall effect. So it's only shown in colloids and also shown in suspension, but colloids are the uh, show the perfect scattering of light. That's why I'm saying that solution is so smaller particles that it did not show the scattering of light. So path of the light is not visible in the solution. So the solution particles cannot be separated from the mixture by the process of the filtration. The solution particles do not settle down when left undisturbed. That is, a solution is stable. Concentration of a solution. In activity 2.2, we observe that groups A and B obtain different shapes of solution. So we understand that in a solution, the relative proportion of the solute and solvent can be varied depending depending upon the amounts solute present in a solution. It can be called dilute, concentrated, or saturated solution. Dilute and concentrated are comparatively comparative terms in activity 2.2. Okay, activity 2.2, the solution obtained by group A is diluted as compared to that obtained by group B. Activity 2.3, take approximately 50 ml water each into separate beakers. Add salt 1 beaker and sugar or barium chloride in the second beaker with continuous stirring. When no more solute can be dissolved, heat the content of beaker to raise the temperature by 5 degrees C. Start adding the solute again. So is the amount of salt and sugar or barium chloride that can be dissolved in water at given temperature the same? At any particular temperature, a solution that has dissolved as much solute as it is capable of dissolving is said to be a saturated solution. In other words, when no more solute can be dissolved, in other words, when no more solute can be dissolved in a solution at a given temperature, so it is called a saturated solution. The amount of the solute present in the saturated solution at this temperature is called its solubility. Okay, so if the amount of solute contained in a solution is less than the saturation level, it is called an unsaturated solution. So what would happen if you were to take a saturated solution at a certain temperature and cool it slowly? We can infer from the above activity that different substances in a given solvent have different solubilities at the same temperature. The concentration of a solution is the amount, mass or volume of solute present in a given amount, mass or volume of solution. Now, there are various ways of expressing the there there are various ways of expressing the concentration of a solution, but here we will learn only three methods. What? Mass by mass percentage of a solution, mass by mass. Okay, mass by mass percentage of a solution. So mass of solute by mass of solution into 100, mass of solute divided by mass of solution into 100. So mass by mass percentage of a solution, how can we calculate? How can we calculate it? Mass by mass percentage of a solution, mass by mass percentage of solution. So mass of a solute by mass of a solution. So it's simple. Mass, if you want to, mass by mass percentage of solution, right? So first take the what they are asking in mass. Take that mass, take that solute, divide by solution into 100, you can get the percentage of a mass. So this is the first formula. Second formula is this volume, I guess. Yes, mass by volume percentage of a solution. Take the solute and under that volume of a solution into 100. That's all. The third is volume by volume percentage of a solution. So volume of solution divided by volume solution, volume solute divided by volume solution into 100. That's all. So if here is a given example, a solution contains 40 gram of common salt, 32 gram of water. Calculate the calculate the calculate the concentration in terms of mass by mass percentage. Mass by mass they are saying, right? So I will take 40 gram of common salt in a 32 gram, and 40 divided by, I will take this is the what is this? This is the solute, and now I'm taking solution. So remember here solute given 40 and common salt, and solvent given 320. Remember solvent, it's not solution, it's solvent. So I will take 30 20 30 60 as solution into 100. Cut. Now 4 za 4 10 za 4 9 za 10 10 100, 1000 divided by 9, right? Yeah, So here is 10 100 divided by 9. So if we divide by 9, 1 the 9, 110, 1 9, 1 point 1 the 9, it will go as like, so 11 point something. What 11 point something? You're doing right. Yeah, I'm doing right. Mass solution, yeah. So 40 divided by 40, yeah, that's the correct answer. I'm taking, so 11.1%. So what is a suspension now? So what is suspension, guys? So non-homogeneous systems like those obtained by group C in activity 2.2, in which solids are dispersed in liquids, are called suspension. Non-homogeneous systems like those obtained by group C in activity 2.2, in which solids are dispersed in liquids, are called suspensions. A suspension is a heterogeneous mixture in which the solute particles do not dissolve but remain suspended throughout the bulk of the medium. So particles of a suspension are visible to the naked eye. Properties of suspension. Properties of suspension. So suspension is a heterogeneous mixture. Suspension is a heterogeneous mixture. Second one is the particles of a suspension can be seen by naked eye. The particles of a suspension can be. The particles of a suspension can be seen by naked eyes. Okay. Because particles of suspensions are very large. Or because I already told you its size is above 1000 mm, so you can see naked eyes. So the particles of suspension scatter a beam of light passing through it and make it path visible. Okay. The solute particles settle down when a suspension is left undistributed. That is, a suspension is unstable. They can be separated from the mixture by the process of filtration. When the particles settle down, the suspension breaks and does not scatter light anymore. What is a colloidal solution? What is a colloidal solution? So now they are talking about colloids. So the mixture obtained by group D active 2.2 is called colloid or colloidal solution. The particles of a colloid are uniformly spread throughout the solution. Due to the relatively smaller size of particles as compared to the suspension, the mixtures appear to be homogeneous, but actually it is a heterogeneous. I already told you, right? For example, milk, because of the small size of the colloidal particles, we cannot see them naked eyes, but these particles can easily scatter a beam of visible light as observed in it. This scattering beam of light is called the Tyndall effect. So here is Tyndall effect. I already told you, right? Frank called it Tyndall effect after the name of the scientist who discovered this effect. Tyndall effect can also be observed when a fine beam light. You already know that how Tyndall effect to do. So Tyndall effect can shown. Tyndall effect can be observed when sunlight passes through the canopy of a dense forest. In the forest, mist contains tiny droplets of water, which act as particles of colloid dispersed in air. Tyndall effect. So particles of colloid. So a colloid is a heterogeneous mixture. The size of particles of a colloid is too small to be individually seen with naked eyes. Okay. So a colloid Properties of a colloid. Colloid is a heterogeneous mixture. The size of the particle is colloid is too small to be individually seen with naked eyes. You cannot see the with naked eyes, bro. Colloids are big enough to scatter a beam of light passing through it and make its path visible. They do not settle down. They left undisturbed. That is a colloid is a quite stable. They cannot be they cannot be separated from the mixture by the process of filtration, but a special technique of separation known as centrifugation can be used to separate the colloidal particles. The components of a colloidal solution are the dispersed phase and the dispersion medium. The solute-like component or the dispersed particles in a colloid form the dispersed phase, and the component in which the dispersed phase is suspended is known as the dispersing medium. So colloids are classified according to the state, solid, liquid or gas, of the dispersing medium and the dispersed phase. A few common examples are given in table 2.1. From this table you can see that they are very common in everyday life. Differentiate between homogeneous and heterogeneous mixture with example. Okay, you can do that. How are solution solute और sol लिखा है. How are sol solution and suspension okay. Okay, here is a mistake in questions. How are this will be how are solution, colloids and suspension different from each other? It will be to make a saturated solution 30 gram and 100 gram of water at 293 K. Find. So here it says to make a saturated solution. Okay, 36 gram of sodium chloride is dissolved in 100 gram of water at 293 K. Find its concentration and its temperature. 36 gram of sodium chloride is dissolved in 100 gram of water. So 36 gram of sodium chloride. So it is a solute given and 100 gram of water given. So 136 is the solution, and it says find its concentration at its temperature. 293 Kelvin means how many degrees Celsius? 20 degrees Celsius. 20 degrees Celsius, right? So if I do this problem here, 293 K means 20 degrees C, and they are given 40 or something, 36, right? 36, what the fuck, 36 divided by 136 into if we do into 100, then we'll get the percentage, but here not set percent, about set. So to make a saturated solution, 36 gram of sodium chloride dissolved in 100 gram of water, right, at 293 K. It's really easy. Find its concentration at this sample. Find its concentration. So you learn about the formulas, right? Where? Here. No, here it is. First one is percentage of solution, mass solution. Mass by volume, percentage of solution. Volume by volume, percentage of solution. But there is no concentration here, guys. So how can they ask concentration? So if I find its concentration, in temperature, if I say what is the formula, then I have to find it out. So mass equal to mass of solid by mass of solution into 100. That's not what I'm looking for. I'm looking for concentration, guys. Water at the mass of solution is 136. I know. Okay. So this is not what you think. So that this 20 says no, it's just shown, it's not used anywhere. You have to find out mass by mass, just like it, just like that. 136, 36 and 100. How will you do it? 6 no, 2 2 1 2 3 2 6 1 2 8 1368 13 2 no. 6 13 6 no. 5 not. So 68. How we also you can cut by 2. 250. 2 3 2 4 now 13 2 no, 2 13 3 3 3 9, no, it will not. 13 4 still 2 2 2 1 2 7 7 and 225. 17 13, we have to use calculator here. If we use calculator like 13 divide by this into 25, 19.11 we are getting here. But if we do 36 divide by 136 into 100, we are getting a different 26.47. Approx 26.47 is the right. Get the approximate. So there is no need for this here. This is just shown and just scared you. So now we're common examples of colloids. We're getting some common example of colloids like dispersed phase, liquid, solid, gas. Dispersed phase, liquid, solid, gas, liquid, solid, gas, liquid, solid. And dispersing medium, gas, gas, liquid, 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 solid, solid, solid. So now first dispersed phase liquid, dispersing medium, gas, type aerosol. Example fog, clouds, mist. Fog, clouds, mist means dispersed phase liquid, dispersing medium. What is dispersed phase means? Dispersed means dispersed refers to the way particles of one substance are spread throughout another in a mixture. Okay, spread throughout. Dispersing medium. Dispersing medium then. Dispersing refers to the medium which particles of another substance are spread out in a colloid. Dispersed phase, the particles that are distributed like fat. Okay, dispersed medium, the substances which these particles are spread. Okay, like water and milk. Dispersed phase, the particles that are distributed like fat globules in milk. Distributed. So dispersed phase and dispersing medium both are different. You have to understand properly. So dispersed phase is where the particles that are distributed like fat globules in milk, where the particles are distributed like in a milk, fat are present, uh, globules, vitamins are present, right? Those are the dispersed phase particles. And dispersed medium like gas, or like here the substance in which these particles are spread, the substance in which these particles are spread like water, milk in water, like water in milk. So liquid, then gas, medium is gas, dispersed phase is liquid, and dispersing medium is gas, and type is aerosol. Example, fog clouds, mist. Solid, gas, aerosol, smoke, automobile exhaust. Now, gas, liquid, type foam, shaving cream, liquid, liquid, dispersed phase liquid also, or dispersing medium also liquid, type emulsion, milk, face cream. Dispersed phase solid, dispersing medium liquid, type sol, milk of magnesia and mud, solute. So dispersed phase gas, dispersing medium solid, and type foam. Foam, rubber, sponge, pumice. Liquid, dispersed phase and dispersing medium solid, type gel. Jelly, cheese, butter. Dispersed phase solid, dispersing medium solid, type solid sol. Example, colored gemstone, milky glass. Ah. Wait guys, give me 2 minutes. Sorry. Sorry. So where are we again? अरे नहीं. Okay, we are in the physical and chemical changes, right? So physical and chemical changes, we'll be quick about it. Physical or chemical changes. Physical or chemical. Physical or chemical changes. Physical, chemical. Wait a minute, guys. I'm coming. कुछ भी हो रहा है आजकल. हाँ गाइस, कुछ भी होता है जिंदगी में. कुछ भी. कुछ भी. चलो, जो बाकी है वो तो कंप्लीट कर लेते हैं चैप्टर. सो फिजिकल एंड केमिकल चेंज क्या होता है पता है? फिजिकल और केमिकल चेंज में क्या होता है डिफरेंस? फिजिकल और केमिकल चेंज. सो फिजिकल एंड केमिकल चेंज में क्या होता है? सो इन द प्रीवियस चैप्टर वी हैव लर्नड अबाउट ए फ्यू फिजिकल प्रॉपर्टीज ऑफ मैटर. So the properties that can be observed and specified like color, hardness, rigidity, fluidity, density, melting point, boiling point, etc. are the physical properties. The interconversion of states is a physical change because these changes occur without a change in composition and no change in the chemical nature of the substance. So although ice, water and water vapor all look different and display different physical properties, so they are chemically the same. So they are chemically the same. So both water and cooking oil are liquid, but their chemical characteristics both water and cooking oil are liquid, but their chemical characteristics are different. They differ in odor and inflammability. We know that oil burns in air, whereas water extinguishes fire. So it is the chemical property of oil that makes it different from water. Mm, mm. Both water and cooking oil are liquid, but their chemical characteristics are different. They differ in odor and inflammability. We know that oil burns in air whereas water extinguishes fire. It is the chemical property of oil that makes it different from water. Burning is a chemical change. During this process, one substance reacts with another to undergo a change in chemical composition. Chemical change brings change in the chemical properties of matter and we get new substances. A chemical change is also called chemical reaction. So during burning of a candle, both physical and chemical changes take place. Can you distinguish this? Wha- What are the types of pure substances? On the basis of their chemical composition, substances can be classified either as elements or compounds. Elements. Robert Boyle. So elements. What the fuck I'm saying? So what are the types of pure substances? What are the types of pure substances? On the basis of their chemical composition, substances can be classified either as elements or components. Okay. So what are the type of pure substances? So pure substances types. So on the basis of their chemical composition, pure substances can be classified either as element or compounds. Elements or compounds. So elements. So Robert Boyle was the first scientist to use the Learn element in 1961. Anthony Laurent Lavoisier, Anthony L. Lavoisier, 1943-94, a French chemist, was the first to establish an experimentally useful definition of an element. He defined an element as a basic form of matter that cannot be broken down into simpler substances by chemical reactions. So elements can be normally divided into a metal, nonmetals, and metalloids. So elements can be normally divided into metal. Elements can be normally divided into metals, nonmetals, and metalloids. So metals usually show some or all of the following properties. So they have a lustre sign, they have silvery. So guys, we're ending the where we last. It's the last is elements. That's so elements. So we are ending the study for today here. Let's meet the next study session or hour. So goodbye. Goodbye.